So just as we had a map for multiple data types last week, we can also make fold-R for multiple data types as well. So the way to see this generalization is to have a closer look at what fold-R does to a list. So if we remember from the last video that fold-R has this kind of pattern that it generates for a list with x1, x2, and x3 and an initial value a. And we can compare this directly to the original list. So what it's done is it's taken the empty list and mapped it to A up here. And then it's taken a list cell with x3 followed by the empty list. And then it's replaced, if you like, the cons operator, this colon, with f, and kept the value x3. And then again here it's replaced the cons operator with f and kept the value x2, and it's replaced the cons operator with f and kept the value x1. So in some sense what fold-R is doing is systematically replacing all of the empty lists with A and all of the cons operators with F, and then evaluating the final expression. So can we do the same for trees? So here's a simple definition of trees. So a data type tree of A's, there's either a leaf or it's a node with a left subtree, a data value, and a right subtree. Now here's a typical value of type tree. So it's a tree which has a 4 at the root, and then the left subtree just contains 1 and 2 leaves, and the right subtree contains 2 and 2 leaves. Now let's say we were going to add these up. So what would happen? Well, you might imagine that every leaf counts for 0. So we're going to replace each leaf with 0. Let's do that in sort of ASCII art. And then we've still got the values in there. So we've got 1, 4, I'll put the brackets around here. And 2. So you can see now we've got the same thing. And then what we're going to do is say that the way we're going to replace nodes is by summing up the values of their 3 subtrees. So we're going to replace each node with a kind of pair of pluses. So the graphical correspondence is not quite as nice as it is for lists, but we can still see that what's going on is that every leaf is being replaced by 0, and every node is being replaced by a sum of its subtrees. So let's try and write fold for trees. So let's try fold tree. And then just as the list one took a case for the empty list and a case for the cons, we're going to take a case for leaves and a case for nodes. And we're just going to write the leaf one first in the type. So it's going to take a B, which is going to use to replace leaves, and then to apply to node, well, let's say we've processed the left subtree, we've got back a B, we've got an A in the middle, we've got to process the right subtree to get a B, and then altogether return a B. And then we take a tree of A's and return a B. Then we write fold tree, where we've got the leaf thing and the node thing. In fact, I'll write it as lowercase leaf, lowercase node. And then when we get to the leaf, we return the leaf value. When we get to a node with left subtree, value x, and right subtree, then we have node. The result of processing, we're going to apply the function node, the result of processing the left subtree with the same leaf and node parameter, the value x in the middle, and the result of processing the right subtree with the leaf and node parameter. So notice this is very similar to the fold-R we had before. So fold-R took 2 parameters, one for what to do when it was the empty list and what to do when it was a cons, and it used the empty list one when it was the empty list, and it used the cons one when it was a cons. Again, we're taking 2 parameters, what to do when it's the leaf and what to do when it's a node. So let's just make sure this type checks. Yep. And now we can do things like write total tree using fold tree. So let's write total tree. Let's say it takes a tree of ints and gives us back an int. And then total tree we can define using fold tree. And now we have to first say what's the total of a leaf, right at 0. And then what's the total of something where we've worked out the total of the left subtree, the value in the middle, and the total of the right subtree. And then we add them together with the left, x, and the right. And if we load that, and then we work out total tree for the tree node, leaf 1, leaf 4, node, leaf 6, leaf. So there should hopefully be 11. So indeed it's 11. And it's not just trees this works for. So maybes it works as well. So again we're going to play the same idea. We've got two cases, there's nothing and just. And in this case there's actually no recursion. So we're not really capturing a pattern of recursion, but we are capturing a pattern of case analysis on maybes. So we're going to do fold maybe. And then we need what to do in the nothing case. And if we've got a value in the just case, then we need a way of transforming those into b's. And we're going to take maybe a's into b's. So this is going to capture a general pattern of got something to do in the nothing case and something in the maybe case. So let's call it nothing and just. In the nothing case, we return nothing. In the just case, we apply the just function. So in some sense, we can read this as returning concrete data, which is a thing that begins with capital letters and is coloured in blue here in Emacs, and turning it into kind of active functions, this lowercase thing here. So in the nothing case, it turns it into the nothing parameter. In the just case, it turns it into the just parameter. And those things may actually do things. So a simple one is a kind of default function. So what's that going to do is going to take a default value in just a maybe, and then the idea is that when the maybe is nothing, it returns the default value. If the maybe does have a value, then it returns whatever it is. And then we can simply write this using pattern matching, but just to illustrate it, we can write fold maybe with the default value, and then the identity function for what to do with just. So if we reload, oops, need to uncomment this definition of maybe, and then if we do default maybe, let's say our default value is exit. If we have nothing, then we exit. If we have just do stuff, then we get do stuff. So this is a way of getting a default value. So now both the trees, lists, and maybes were all kinds of containers. And last time we looked at this with string, which is a kind of infinitary container containing a value for every string. So how did that look? So we had with string of a is really functions from strings to a's. And we saw last time we can define a map for this. So could we define a fold as well? I mean, does everything that has a map, or is it sort of container-like, does everything have a fold? So there isn't really any way of defining fold for this data type, because there's no way of adding up the value of a for every string. So, for example, we defined this length, which was a value of with string, int. And then what was length? Well, it says with string, for every string, it returns its length. So we can try and use this to work out the length we can think of it as a container which contains the length of every string for every string. But there's no way of adding up the lengths of every string to get a number, because this is an infinite, there's infinitely many strings. So we can't define a fold L or fold R for with string. So in summary, fold R-like functions can be written for other data types. And it's interesting to try and write a fold L as well, and it's not actually possible for things like trees. And this captures common patterns of recursion on those data types. So things like working out the total of the tree, or getting default values from a maybe. And not all data types have a fold, even if they have a map. So this usually happens if they're kind of infinite data types, like with string.